let us examine all the different possible outcomes that you can have by reaction of chlorocyclopentane with chlorocyclopentane there with sodium ethoxide. Sodium ethoxide. So that is sodium plus, and the counter ion of that is the conjugate base of methanol, right? And let's say that you run the reaction in a solvent like methanol. Well, you know that methanol, because it has an OH, it can form hydrogen bonding, right? So it has very, very well-known characteristics. Well, when you perform the reaction of chlorocyclopentane with sodium methoxide in methanol, the products that you will get will be cyclopentene. Pentene is this, and you will get the substitution product as well. And when you look at the percentage, the distribution of the products, you will see that the major product is the elimination product, while the substitution product is the minor product. How about if you run the reaction in a different solvent? Let's say you run the reaction in DMSO. DMSO stands for dimethyl sulfoxide. Dimethyl sulfoxide, and that is the structure of dimethyl sulfoxide. Sulfur oxygen double bond with a couple of methyl groups on the sulfur. Once again, I am using sodium methoxide as a reagent, but with a different solvent. And surprise, surprise, the product distribution is just about the opposite. You will get the alkene as the minor product, and you will get the substitution product as the major. So what is going on here? How come that you get different products when just changing the solvent, and not only you get one product, but you get two products every time? Well, the reason is that here we are dealing with the competition between different mechanisms of reaction. You see, the major product that you get with the reaction on top, that is actually an elimination product that is produced by an E1 elimination mechanism. While the minor product that you get, this is the substitution product that is derived from a mechanism that goes SN1. It will be an SN1 mechanism. And then at the bottom, we have the minor product will be the product of an elimination with the mechanism that goes by E2 elimination, while the substitution product will be a substitution that goes through an SN2 mechanism. So we need to get a good understanding of all these different types of mechanisms. What does it mean? SN1, SN2, E1, E2. Well, we already said before that the number 1 or 2 indicates the molecularity of the reaction. So that means it's telling you how many of the species are involved in the formation of the transition state in the reaction. The fact that the two reactions on top are E1 or SN1, that means that the rate of the reaction depends on the concentration of only one of the reactants. And that reactant in particular is the substrate, right? The concentration of the substrate, that is what will determine the rate of the overall reaction. While in the second case, the rate of the reaction depends both on the concentration of the substrate and the nucleophile or the base. It depends on which reaction, which product you are looking at. This will be when methoxide is acting as a base. This will be when the methoxide is acting as a nucleophile. So let's examine each one of these different mechanisms of reaction to learn more about them. So let's go first to have a look at the so-called SN2. So what does it mean, SN2, in terms of kinetics? That means that the rate of the reaction is equal to a constant. I didn't put the constant there, the constant times the concentration of the substrate and the concentration of the nucleophile. So and that will have some important consequences when I change the concentration of any of the reactants. For instance, if I double the concentration of the substrate, what is going to happen with the overall rate of the reaction? If I double the concentration of the substrate, but I maintain the same, I have the concentration of the nucleophile that remains constant. So in that case, the effect will be that the rate of the reaction will double, right? Because I'm doubling the concentration of the substrate. And then now, how about if I triple the concentration of the substrate and I double the concentration of the nucleophile? What will be your guess? What is going to happen with the overall rate of the reaction? Well, you guess right. So the overall rate of the reaction will be times 6, right? Because you are doubling one and tripling the other. So that's the way it works for the kinetics. So then from here, I will jump to slide 11 here. So what is the mechanism for this reaction? So the mechanism for the SN2 involves what we call a backside attack. So here you have the OH is attacking the substrate, the 2-bromobutane, from the opposite side from where the bromine is departing. So simultaneously, at the same time that the OH is approaching the carbon atom, the bromine is departing. So if I was going to describe what is happening in this overall process, I would say, well, you have the nucleophile OH minus that is attacking from the opposite side of the departure of the leaving group. And the leaving group is the bromine, the bromide, the Br minus. That will be my leaving group. And then half the way of the reaction, you can see that we have a transition state where the OH is, we have a partially made bond between the OH and the carbon, and we have a partially broken bond between the carbon and the bromine. And then finally, when you go to the formation of the final product, you can see that the OH got attached from the opposite side. The bromine is totally out. And interestingly, there was an inversion of the configuration. You can see that we started with the S isomer and we obtained the R product, right? So there was an inversion of the configuration. So rate law, we already know that. If you double the concentration of the nucleophile and double the concentration of the substrate, so the overall rate of the reaction will be times 4, right? So you can predict that very easily. How about the steric effect? What can I say about how much of influence will be by the nature of the R groups that I have here? Well, you can already guess that because the approach of the OH is from the backside, it will be more convenient to have groups that they are rather small, right? And so if I have something like just hydrogen atoms, if I have only hydrogen atoms, so then the reaction will proceed easier, right? So I have my leaving group here, and the nucleophile is attacking from this side. If I have small things here, just hydrogens, it will be easy, the approach. But if I have, instead of hydrogens, if I have terbutyl groups, forget it. That reaction will never happen because the approach of the nucleophile to that carbon will be virtually impossible. Okay, I will stop here and we can